8. So you can remember it could not even send a unit, maybe a 1, a 0, it could not. It has to do it twice for it to be able to send a single byte. So you can imagine how slow or how inconvenient this was. But that was then. Nobody was so much in a hurry of speed, and the development was ongoing. So the chip was developed by Federico Faggio at Intel, which was launched in 1971. So then they came up with the processor, the i4004. And actually, during the same time is when the Intel microprocessor also introduced their first actually theirs was 4004 chip. So it was actually the same time that Intel produced an embedded based chip, but at the same time they produced the microcomputer chip, which was the first commercial standalone single chip microprocessor. So if you look at the structure of i4004, which was the very first, if you look at the scales on how the microprocessor's development has been taking place, you'll realize the very first microprocessor that was developed by Intel was 4004. Then it went down to 4008. Then it went down to actually went down to 4006. Then it went down to 4008. And then it's whereby we started having what we call the Intel cores and so on. So before that, there was just Pentium. No, after that, it came with what we call Pentiums. There when the Pentiums came up, and we started having 4064 version, then 4164 version, then 4364 version. So basically what happens that Intel has a mode in which they will be able to use to cap in terms of marking their processors with kind of serial numbers, but the serial numbers could also be used to determine how the microprocessor is designed, the architecture of the microprocessor itself. So if you look at the structure of 4004, it's a 4-bit CPU for use in electronic calculators. The 4004 was able to address 4K of memory, operating at a maximum clock speed of 740 kilohertz. It didn't even reach 1 million instructions per second. It requires at least 3 additional chips. So a 4001 ROM, a 4002 RAM, and a 4003 input-output interface. So this just basically on how the microprocessor is designed. So in 1980s to 1990s, there came a microprocessor. The Intel came up with 8080 that eventually evolved into the famous 8086 Pentium series. So the Zilog, the Z80 Motorola, the 6800, and the MOS 6502, this evolved to CPU size of 16, 32, and 64-bit design through the 1980s, 1990s, and now a day there are specialized CPUs of up to 128 bit of width in terms of operations. So as I will still say that you really need to understand the architecture of computer systems. That is the only time you'll realize that where do we come, or what is it that when we say that the microprocessor size is 16 bits, when we say the microprocessor is 32-bit, and when you say the microprocessor is 64-bit. What does all these things mean? And you can see currently the microprocessors which are being designed, they are what we call a 128-bit. So basically these are the register paths. These are the speeds that the microprocessor would be able to operate within its logical zones, to be able to work with the clock speed, the logic speed, the data speed, and actually there are 3. We have the data addresses and the address speeds. So once you understand how the address speeds work, how the logic, the control speeds work, and how the data bus work, then you'll be able to understand what do we mean by 16-bit, what do we mean by 32-bit, and what do we mean by 64, and currently, what do we mean by 128-bit width. So the lag in the microprocessor control. So the application for the embedded system have been dominated for decades by up to 8 16-bit microprocessor. So what that means is that most of the embedded systems are just falling backwards in terms of the speed of the bandwidth or the width of the data controls within its center. So that means it can only work with a max of 18 bits. We still don't have the microcontrollers that would work up to 64 bits. I know the designs are already there, but currently what we have or dominates the embedded systems are between 8 bits and 16 bits of the microprocessor. So further in the 90s and 2000, microprocessor applications are now complex. They require applications to be broken into several interactive embedded systems. So the modern systems, the multimedia player, it has the audio input, output capability, the digital camera, the video processing system, hard drive, a user interface key, touch screens, the graphic displays, power management and digital communication components, each supported by individual embedded system. So you should actually understand that the embedded systems is implemented in piecemeal, whereby it can be implemented only on the audio part of your system. It can only be implemented only on the digital aspect of your system, only on the storage part of your system, only on the graphical part of your system. So it depends on which, how that particular industry or the manufacturer of that particular equipment would want to bring in the embedded system on each and every equipment that they are making. So one of the things you fully need to understand that embedded system is actually also within our computer system that they are using, but they are actually implemented as a unit, maybe for a specific part of the computer systems. So all of them are non-user programmable, and all of them are embedded within the application, and their operation require minimal or no human intervention in terms of operation. So in 2000s onwards, there have been a wide use of embedded system, and the embedded system can be found in almost everything, as we had seen in our very first classes, in our day-to-day life, and we had seen in toys, in phones, almost in everything that we touch today, and it is digitally having a digital aspect of technology, then you should remember that there's some aspect of embedded system in it. So they are virtually in every aspect of our modern life and are ubiquitized devices, but almost are also almost invisible to the user. So what basically happens is that you might not even be aware that you are having embedded systems implemented on the equipment that you're having, because some of them are actually hidden. But at the end of the day, they bring in the operational of that particular component at the end of it all. Okay, so I would pause there and would get back to you if anybody has a question or there's some part or aspect that you need me to further explain. Any question from the students? Anything that is not making sense in terms of the history of the embedded systems, in terms of the architecture of the embedded systems and the computer systems? And actually, we are doing them side by side. We are looking at the computer system architecture, and at SuperV, we are also looking at the embedded system architecture. So I'll pause there and would want to listen to your questions, get questions from your end before we continue. Any question? Gregory, do you have a question? Gregory.
No, I don't.
Okay. You have more than one appliance on, or it's only one? Okay. Derek Kipruto, any question? And by the way, Gregory, this class needs to have a max of how many people? Gregory.
Yes, around, we actually supposed to be around 84, 85 there.
84,
But
85.
yeah, but for today, most of us had thought like we were to have the class physically. So probably some are on transit. I don't know. Ama some or they plan to go back home.
Physically means we'd have the quorum, meaning that I hope there's internet in the university. Is it? We should try and attend class because this is half. It's too few. I mean, we need to have at least 50 or 60 students in class. Anyway, it's okay. I was just filling questions to be able to see if somebody has a question. If there is none, then I think I will continue. So there is an exercise there, and I would always want you to sketch something on this. I would always want you to put down or take time and do these exercises. They are always a pillar for me to utilize when it comes to cards and giving out assignments to students. So I would always advise that please take note of this assignment. And may I ask, are you able to see these particular slides on your classroom?
Yeah.
Okay, thanks. So I would want you also to have time do these exercises. I would not want a scenario whereby I would want you to submit them for me to have a look at them, but I would want you to take them upon yourself and look at it. Like, for example, you give a sketch of how embedded systems have been involved with time. I think this is something very nice if you would be able to have time and look at it and see the development of embedded system in a sketchy mode. You'd also discuss how you expect embedded system to evolve in the next 20 years. Yes. So this would also be such a very wonderful kind of, but then today we have so many applications that could be able to help you predict how the system evolved will be in the next few years. So you should take advantage of these particular systems whereby you'll be able to structure and see that in the next 3-4 years, this is the level of embedded system. And this would be able to advise on what needs to be put in place to enhance the development of equipments. Okay, so I'll continue and look at the embedded system design and paradigm. So basically, embedded system has what you call the input-output components, the mouse, the keyboards, the sensors, and so on. This is what we refer to as the system inputs. Embedded system also has what we call it software. So the embedded software components, hardware components come in there. So this is where we have the microcontrollers, we have the ROM, we have the RAM, and so on. And then the output is the system output. So this is where we have what gives us, we have the LCD screens to give us the output and the servo motors to turn and so on. So we need to understand what is the design of the embedded systems and how is it structured. So if you have a look at that, so the input output devices, sensors and so on, then the control action actuators and so on become the output devices, the lead, the LCDs and so on. So embedded system design paradigm. So if you look at the hardware components, this is where we have the CPUs, we have the input output, the memory, program the data, the communication ports, the serial ports, the parallel ports, user interface, the keypads, maybe the one for putting in the code for you to access a safe or a building, switch, a buzzer, the audio lights, the graphic displays, the sensors, the electromechanical actuators, the data converters, the analog to digital, the ADCs, the digital to analog, the DACs, diagnostic and redundant components, system support components, other option support components, e.g. timers, interrupts managers, logic, DMA, controllers, application-specific integrated circuits, ASIC, and the field programming of gateways, uh, FPGAs. So all these are hardwares that are actually utilized in the embedded systems. So some are basically the inputs, some are the outputs. When you look at the software components, all the programs necessary to give hardware functionality, the operational system, it varies from one operation system to another, then the real-time operating systems. So as we are seeing the different types of embedded system in our last class, we did talk about what we call the real-time Arduino or the real-time microcontrollers. So the real-time microcontrollers would use what we call the RTOS. So that is the design of the embedded system. There's the user interface. There's the interconnect of the hardware between the CPUs, the memory, and the ports. We have the analog digital converters, digital analog converters coming down here. Why do you think we need these converters? Why do you think they are very important in an embedded system? Anyone who would be able to answer that? Why do we need the analog digital converters? Can anyone take a guess?
To be able to read continuous data, because not all sensors provide digital data.
Okay, I think that's fair enough. So the analog digital converters are very important because when you are feeding in an analog data, this is a digital environment, and the digital environment needs something that will be able to get it into a structure that it can consume it. So the analog data has to be converted into digital for the computer system, which is digital, to be able to consume it. The other way around, the computer has processed something and would want to give an output, which is an analog signal. So we'll need a digital to analog converter to be able to have what has been processed. And if you can look at this screen, this ADC gets into the hardware interconnection, and then the DAC gets out. The arrow here tells us DAC because the CPUs is both in and out. These are the ones. So you can, our arrow systems here would be able to tell you clearly what is the function of the ADCs and what is the function of the DACs, correct? So the sensors and the signal conditioning, these ones, they're analog, but they have to be converted into digital. And actuators and drivers, they're also analog. So, but the output here is digital, so it has to be converted back to analog for it to be consumed by the end devices. So this particular structure is very, very important, and you need to understand. So if I give you an example in a cart or something, then I tell you, I would want you to explain for me an embedded system using a design. So this is what I expect to come from you. So system task application software. So big programs split into small programs. So that's what we call a task. A task handles a distinct action in the system. So a task requires the user of specific system resources. Tasks submit services requests to the kernel, and in order to perform their designated actions, so service requests can be placed via a registers or an interrupt. So most of you, since you're growing and within the computer science, what happens mostly, we do a lot of system development. And in that particular scenario, I don't expect anybody to have an issue with what a task is when it comes to system application, and more so to embedded systems. System kernel. System software. So a kernel is a software that handles the system resources, correct? So what are the system resources? So the kernel actually is what ensure that it sits right at the center of the processor, and basically its work is basically, and more so, the kernels can actually be reprogrammed. You can be able to tell the kernel what you want it to do. So it's a software that handles the system resources, the resources that are within the embedded system. This is the output resources, the input resources, and the compute resources. So example of system resources are the memory, the input-output devices, the CPU itself, and the other components of the computer. So the kernel. So where does the kernel sit in terms of a functioning system? Who knows where it sits? Does it sit within the hardware? Does it sit within the software? And which software does it sit on? Anyone who tell us where the kernel sits? Yes? Where does the kernel sits on the entire computer system? These are questions I'm supposed to ask the first year, not third years.
I think it sits between the hardware and the operating system.
Okay.
Yeah,
Yeah.
and it's an interface.
Yeah.
Between
So
the,
basically, the kernel sits in there. And in most cases, the kernel comes in with the operating system, because it's the operating system that would be able to tell the hardware what to do. So without the operating system, then you cannot be able to interact. You cannot be able to interact with the hardware. So in a nutshell, it sits between the hardware and the software, but what brings the kernel into the picture is the operating system. So when you do, and when you understand the operating system in deep, you'll be able to see that it is the operating system that brings in the aspect of the kernel, because it is what will come in to be able to understand what resources is needed by the operating system. When should the mouse move? When should the mouse stop? When should I impute? When computer should be able to give me an arithmetic operas, and so on. So basically, you'd want to understand where the kernel sits and what is its function. So the kernel receives services requests from the tasks, and we've seen what a task is. So the kernel schedule a task according to the priority provided by the tasks manager, and a resource manager policy is used to resolve the request competing for the same resource. So all this we are talking about kernel, I believe you learned them in the operating system. So when you are doing a course called operating system, this was the time to master how all these functionalities are brought into place. So I believe you should be at par with that. And since most of you are actually planning to be developers, even the guys who are planning to be to do automation of the infrastructure and so on, we have you really have to understand how the kernels work and how the kernels be able to share and become the the central manager or the source of policies that would be able to resolve several interrupts within the functioning system. So apart from the tasks, you also need to know what is a service. So services, routines, served the tasks. So service routines serves the task. So we've seen kernel is a software that handles the system resources. Service routine, these are the code that gives functionality to any system resource. In other places, it's also referred to as the device drivers. In other places, it's also called the third-party software. So you really need to be able to understand what is a service routine when it comes to the embedded system. The codes that gives functionality to a system resource, and in other places, it's also called the device drivers. And I've also said in other places, you can call them as third-party software. So when you are having a system and it needs a third-party software, then in this case, we are saying it needs what we call a service routine, it needs what we call a device drivers, or it needs a third-party application that would be able to tell the operating system that the hardware that I'm putting on board, the mouse I've added, the adapter I'm putting in place, the screen I'm adding to extend this particular screen needs to work with that. So it's a mouthpiece between the kernel, the operating system, and the hardware. So that needs to come out very clearly. So services can be activated by pulling or as an interrupt service routine, ISRs. So all these, I believe, from my point of view, you should be able to understand what they are. Okay. So embedded system design process. So there are types of embedded systems, which is very important. We have what we call a standalone embedded system. We have what we call a real-time embedded system. We have what we call networked appliances embedded system and mobile devices embedded systems. So each and every type of embedded systems is implemented in its own way. So the main elements of embedded systems, this should now be very clear from our subsequent classes. One, the processor, the microprocessor, the microcontroller, and then the digital signal processor. So you really need to know each and every component or each and every element of embedded system. What is a processor? What is a microprocessor? What is a microcontroller? And what is a digital signal processor? So the design process continue. So there's abstraction, the problem related to the system is identified. Hardware, software architecture, know the hardware and the software component well that you'd want to use. Extract functional properties, extract functional to be implemented, understand them well from the main design. System related family of design, refer to a previous system related family of design. So this is there a previous design that was there, and what were the shortcomings and what were the best part of it. Modular design, use a separate modular design approach for later reuse. Mapping, software mapping is done, data flow, program flow, and mapped into one. User interface design, so depend on user requirement, environment analysis, functions of the system, e.g. reducing power consumption, mobile and so on. So refinement, components and modules are refined appropriately to optimize performance. So this is just a design process of an embedded system. So if you are to design an embedded system, then this is the process that you need to go through. As you design the embedded system, you really need to get the history of the embedded system. You don't just design. You'd want to go through all these processes to be able to come up clearly with a well-oiled embedded system. So the important thing to note is that in embedded system design, one has to understand the separate design activity for hardware design and for software design. Best if a standard methodology is followed, e.g. the waterfall method and so on. So integration, interfacing the design, how do you interface the software and the hardware from your design? So I'll pause there again and get a feedback from your end. If there's any question, any aspect that is not clear, I would explain. So I give you a second or two. Again, you also need to look at the exercises, like one, which is here. Identify the hardware components of an embedded system. Investigate and find out the detail of hardware components in part 1 above. So the detailed component of hardware component of an embedded system. Describe the components of an embedded system. Describe the software components of embedded system. Describe the desired design process of an embedded system, which we have just looked at. And I would want you to pay more attention on the description of the design process of the embedded system. To me, it is key. Like each and every student should be able to understand the subsequent steps that would help you have a well-oiled process of designing an embedded system. So that number 5, I say it is key, and you have to look at it on your own, figure out what are the main processes, what are required to be able to build a workable embedded system. So the programming interfacing of the embedded system is also a bit sketchy, and actually it requires a lot. And this now gets back to how do you write a program, and as you write the program, how do you interface the program with your embedded hardware, and at the end of the day, what is the goal? What's the goal at the end of it all? So from the programming process, if you look at this, you can see the header file, the source file. So mostly from the programming point of view, you understand the importance of the header files. If you're doing C#, C++, you know the importance of the header files, which we shouldn't be able to discuss in this class because this is well articulated in all the languages that you're learning. We have what we call the source files, and the source files here is basically what you're bringing in. So the two meet at a preprocessor zone, and then it has what we call the process source file. Then there's what we call the cross compiler. Both goes up to the end. Then when I think this was taught by Professor Bade, if I'm not wrong, or is it the object-oriented language and so on, whereby we have the linkers, the linker scripts, and so on. We also have the programmed target, the program target with the programmer. We have the binaries, the hex files, the bin, the executable files, and the locators. Locators here are very important because they are part of the memories that actually knows they are meant to learn what the programmer wants, and every other time they would be able to execute the required aspect of the code to give an output. So as developers, this is a cycle that I believe you are more proficient in, and you'd be able to work with it and understand it far much in detail, even more than I do. But my main aspect here is just to see where do we run the embedded program. So the embedded program is run as a programmed target. This is whereby you would be able to know, you are the one telling the embedded system, what do you want to do? Or what do you want to execute? Do you want the motor to run? Do you want the LED lights to come up? Do you want to produce the word, I love this class on your screen, and so on? So where does that goes in? So basically that goes in on what we refer to as the programmed target. And that is where the embedded system will be able to set in the whole programming process. The programming environment. The programming environment, you have the peripheral interfacing via assembly language. Once that is done, then we have the microcontrollers, the microprocessors, assembly language, user outer world complied languages, interpreters, languages, C++, and so on. So basically, these are the environments. So every time you are looking at the peripherals interfacing, the language is assembly. Look at the microcontrollers, the microprocessor, the language is assembly, C++, C. The user interfacing, it has quite a lot of language that can be able to be utilized to handle that aspect. So further in the programming language, at third year, you understand what we call the server side, the client side aspect. So you'll be able to know what runs on the server side, the backend, what are the languages that can be utilized to program the backend. How many of you have ever been able to program using Ruby on Rails? Or is there any student who has an interest on Ruby on Rails in this particular group? Yes, is there anyone with interest on Ruby on Rails? Anybody? Yeah. So I would ask you, create some time, look at it. Ruby on Rails is such a very interesting programming language when it comes to development of writing applications that can be controlled more so by Arduino systems. So should I look at it and get the beauty part of Ruby on Rails. So on the client side, the common norms, the CSS, the Javas, the HTMLs, and so on. For microcontrollers, the microprocessors, the interfacing, I'd say it's the assembly language, the C++, the C# and the Java could also actually be used. So what we are looking at here are only the embedded languages that could be able to use on which part of the embedded systems. If you want to do the server side, you know the language to be able to use. If you want to use the client side, if you want to use the program or the control aspect that will control the microcontrollers, the microprocessor, and the processor themselves, then you should also be able to tell which language are you looking at in this scenario. So again, as I come down these sides, this is still where your programming skills would be able to measure. So we have the IDEs and the SDKs. So the wireless microcontrollers, the single software development environment to deliver flexible hardware, software, and tools for Bluetooth, Zigbee, and multi-standard. So the Wi-Fi's and so on. So if we were to do some kind of a design, or would want to run programming environment where we'd be able to implement a wireless access, a Bluetooth controller to be able to work, then we need to look at what we call the SDKs and the IDs that would be able to help us do that. So the wireless microcontroller for a wider variety of ultra low power and real-time control solutions. The reason why we are looking at these ones is because the embedded system is a wider environment. We would want it to control some wireless connectivity. We would want it to control some remote access of a specific components or device. So it's always good to be able to say, where are the environments that would be able to allow us to do all these things, correct? So this is the reason why we need to look at the wireless microcontrollers. We need to look at the processor SDKs. So these are code across processor family for reuse and migration across devices, correct? So if you look at other processors like Citara and Jacinto, which are very, very interesting in terms of cross-platform. One of the things I would always ask students is try and look at this type of processors, the Citara and the Jacintos, and see what do they have, time division appliances, and so on. They are very, very, very interesting types of processors, even though they are not widely used, but you can be able to see how they work and what are some of the languages that they are used to program them. So others are iOS SDK, Java Development Kit for Android, Cloud SDK for Google, and so on. So these are some of those languages that we need to look at when interfacing some components with our embedded system. So I have another exercise there, pretty long exercise that I would also want you to put your hands on. We want to discuss the notion of server-side programming. I discuss the notion of backside programming. What are the languages? What is it all about? What is achieved by both the server-side and backend programming? State at least 5 programming languages for the server-side and back-end programming. And to discuss the notion of client-side programming, notion of front-side programming, which I believe all of you are aware of. What is the achievement? Of client-side and front-side. 4 programming languages for client-side and front-side or front-end environment. So discuss languages for programming, control, interfacing, microcontrollers, and microprocessors, which we have actually seen during this class. Select one server-side and one front-end programming language and learn them well. Remember, I was asking guys who are interested in Ruby and Rails, need to do it well. Kotlin, we say that is a language. So I expect by now you've started learning Kotlin on your own. I'm not going to teach programming, and you know that. But we'd want to have applications developed on Kotlin and so on. Discuss the role of IDs and SDKs in embedded system programming. As we had seen, IDs and SDKs are very important. They help us interface other secondary peripherals into embedded system. State some IDs and SDKs for embedded system. Then familiarize yourself with some IDs for embedded system. So that's an exercise that would be able to help you understand this particular class for today. And you can cover all those 13 questions and then ask yourself whether you understood that class well. Then I think you will be in a good place. So I will pause there for questions. Any burning issue from the class? Okay. So I'd want you to ask questions. or I will ask you from my list here. Joel, Deda, do you have a question? Okay. Ngugi Jerry, any question?
No question.
Okay. David Manga. David Manga.
No question.
No question from you. Alex, do you have a question?
No.
No. Okay.
No problem.
Yeah,
Bear
but
James.
Lawrence has said hi to you.
Thank you.
No question.
No question. Wisdom.
No questions.
Okay. Fidel Onyango, any question? Fidel? Omondi Hansel. Can you hear us? And this guy is here. Okay. So if there's no any other question, I think we will stop in there. We'll stop in there, and the class rep, I have not seen the shared list because we agreed that by end of day today, we should have the Excel sheet with the students who have selected various projects closed. So I expect to get the Excel list today, and the projects that students have picked, I get note of the project that students have picked, and I expect that the project should begin so that we do not have a problem whereby when we're about to finish starting our assessment, then somebody will say, I was not able to join a group. So that needs to be fixed today. And by end of today, I would want to receive that list, which is sealed, so that we start following up with we start moving on with the projects. Unless there was some challenges picking the project, and we did agree that all projects, if you are not able to get the physical component, then we have the Tinkercad application software that is very flexible in terms of implementation of those applications. So I would want to stop in there if there's no any other further question. So